Number 3. Prove that n cubed plus 2n is divisible by 3 for all n which is an element of natural numbers. First step, verification. If n is equal to 1, is this value divisible by 3? So we replace n by 1 and simplify. 1 cubed is 1, plus 2 times 1 is 2. So 1 plus 2 is 3, and 3 is divisible by 3. When n is equal to 2, the value is equal to 12. 2 raised to 3 is 8, plus 2 times 2 is 4. 8 plus 4 is 12, and 12 is also divisible by 3. Next step, we assume that the statement is true for a natural number k. We have our inductive hypothesis k raised to 3 plus 2k. If n is equal to k, then this is divisible by 3. Our challenge is to prove that it holds for n equals k plus 1. If n is equal to k plus 1, then k plus 1 quantity cube plus 2 times k plus 1 is also divisible by 3. Here, we just replace k by k plus 1. Here's our proof. We copy this expression, then manipulate. First, expand k plus 1 quantity cube, and that is equal to k cubed plus 3 times k squared plus 3k plus 1. K plus 1 quantity cube is equal to k plus 1 times k plus 1 times k plus 1. Multiply the first two factors, we have k squared plus 2k plus 1. K times k is k squared, k times 1 is k, plus 1 times k is also k. So k plus k is 2k. Then 1 times 1 is 1. Then multiply this factor by k plus 1, and that is equal to k cubed plus 3k squared plus 3k plus 1. You just distribute each term to k plus 1, then simplify. Or, we can use the cube of the sum of the two terms, which states that x plus y quantity cube is equal to x cubed plus 3x squared times y plus 3x times y squared plus y cubed. Here, our x is equal to k, while y is equal to 1. So we have x cubed or k cubed, since we let x be equal to k, plus 3k squared times 1. We let y be equal to 1, plus 3k times 1 squared, plus y cubed or 1 cubed. Again, we let y be equal to 1. Simplify. K cubed plus 3 times 1 is 3k squared, plus 1 squared is 1 times 3k is 3k, plus 1 cubed is 1. Then we distribute 2 to k plus 1. We have 2k plus 2. Combine the constant terms, 1 plus 2, which is equal to 3. Here, we have our inductive hypothesis k raised to 3 plus 2k. So we group them together and just copy 3k squared plus 3k plus 3. Here, we can factor out 3. We copy k raised to 3 plus 2k plus factor out 3 and copy k squared plus k plus 1 since we factored out 3. This factor is divisible by 3 from our inductive hypothesis. K raised to 3 plus 2k is divisible by 3. And this is also divisible by 3 because it has a factor of 3. Then we let k cubed plus 2k be equal to m, and k squared plus k plus 1 be equal to n. We have 3 times m. Remember, from our inductive hypothesis, k raised to 3 plus 2k is divisible by 3, plus 3 times n. Factor out 3, and we now have 3 times the quantity m plus n. And clearly, this is divisible by 3. Therefore, the statement is true for all counting number n by mathematical induction. Important note: mathematical induction is conducted using 3 steps in its proof. These steps have to be followed in sequence. If a step fails, then there is no need to continue to the next step in order to finish the whole proof. A failure in steps 1 or 2 will already disprove the formula.